Open-o3 video, grounded video reasoning with explicit spatio-temporal evidence. That's the paper we're diving into today. And the ambition here is pretty high. Take that verifiable evidence-based reasoning we've seen for images and make it work for video, the messy dynamic stuff.
Exactly. Open-o3 video isn't an agent, it's a framework. And it really pushes the state-of-the-art by changing how video evidence gets used. It brings an explicit spatio-temporal grounding. So we're talking precise timestamps, actual bounding boxes, object regions, all plugged directly into the reasoning process itself.
Which is a big step up from just getting a text explanation.
Huge step. Moving from those sort of opaque text-only rationales to actual verifiable evidence, and you see it in the results. On V-star, which is a really tough benchmark designed for this kind of precision, they got massive performance jumps. We're talking plus 14.4% on MAME-M, that's multi-choice answer match, and plus 24.2% on MLGM, which is the grounded evidence match metric. That's compared to a strong baseline, Quen 2.5 VLBL.
Wow. Okay, so how'd they pull that off?
Well, it really comes down to two main things. First, curating two really high-quality data sets, STGR COT30K and STGR RL36K. And second, a cleverly designed cold start reinforcement learning strategy. That strategy uses some novel rewards, too. Adaptive temporal proximity and temporal gating. We'll definitely dig into those.
Okay, let's unpack this then. We've seen image models like the ones that inspired that O3 name,
Right.
They can point to the exact pixels that back up their answers. Why has it been so much harder to get that working for video? Why is video reasoning still, struggling with that kind of precision?
Yeah, it's fundamentally about complexity multiplied by time. An image is static, a snapshot. Video is dynamic, it flows. So for video, the model needs to do two really hard things at once: track things over time and locate them accurately in space.
Right, across scenes that are constantly changing. Things move, things get blocked.
Exactly. Occlusions, camera shifts, objects changing appearance. The model can't just spot an object once. It has to track its existence, its state consistently across potentially minutes of video. It's a much harder task.
So if I ask a standard video model, something like, why did the vase fall? It might figure out the text answer. Maybe the cat knocked it over. Yeah. But it probably can't tell me exactly when the cat appears in the, say, 30-second clip, or where on the shelf the vase was right before it fell.
Precisely. Most older video reasoning models just gave you that text trace, the what, but not the when or the where for the visual proof. And the problem there is, without those spatio-temporal coordinates, the reasoning isn't really verifiable, is it?
No, you can't check its work.
Exactly. If the model says the cat did it, but visually it was the dog, you'd never know just from the text. Previous attempts often gave text-only reasons, or maybe coarse timestamps, like between 5 and 10 seconds. But that just doesn't cut it for the kind of fine-grained, verifiable proof needed for benchmarks like V-star, which specifically test linking answers to the right evidence.
Okay, so looking at the problem this way, Open-o3 video basically had these two big hurdles to clear before they could even think about hitting those state-of-the-art numbers.
Yeah, two foundational hurdles. First, like you said, the data gap. There just weren't good enough data sets out there that had synchronized, detailed spatio-temporal labels tied directly into the reasoning steps. You might find rough time info or some bounding boxes, but not usually both, linked cleanly in a structured thought process.
And the second hurdle sounds more like a training nightmare. I mean, even if you have the perfect data, getting a model to actually use two different coordinate systems, space and time together, without messing up, that sounds tough.
Oh, it's a major stability challenge. Training a model to locate things in time and space at the same time, well, it often stalls. Or you get this collapse where it gets okay at one thing, say time, but then completely fails at the other, like space, because the first prediction was slightly off.
Right.
So yeah, this paper really tackled both. First, creating the evidence needed. Second, designing a training strategy specifically to avoid that kind of optimization collapse.
Okay, let's dig into the data part first then. Their goal was transparency, moving beyond just text answers to something you can actually check. How did they build this new synchronized data they needed?
They were very deliberate about it, focused completely on quality, not just piling up huge amounts of data. They built two specific data sets. STGR COT30K for the initial supervised fine-tuning, the SFT,
right, and
STGR RL36K for the later reinforcement learning stage. But the real key, the core innovation, was creating 5,900 new annotations, really high-quality spatio-temporal samples. Then they mix these in with existing data to get good coverage.
5,900 actually sounds kind of small in the world of big data. But you're saying quality was the absolute focus. What makes them high quality in this context?
It's all about the structure. It's not just question-answer pairs. Each data point includes the question, the answer, sure, but also time-stamped keyframes, precise bounding boxes, and a very specific structured chain of thought.
The chain of thought.
Yes, and it's structured rigidly. The model can't just imply the reasoning. It has to explicitly link the visual evidence, the box, and the time to the reasoning steps using this exact format. Object name man, object box coordinates, box at timestamps.
So it's literally forcing the model to cite its sources visually.
Pretty much, yeah. Cite the frame and the box location.
I like that they detailed their annotation pipeline. For anyone actually trying to build structured visual data, seeing the methodology as gold, how did they make sure everything, the box, the time, the text, was actually clean and lined up?
Yeah, that pipeline was smart. It was basically a 3-stage filter designed to catch errors. Stage 1 was data preparation. They used Gemini 2.5 Pro to get initial structured annotations in JSON format.
Okay, sort of bootstrapping it.
Right. Then stage 2 was bounding box filtering. And this part is quite neat. First, they threw out obvious junk like boxes that covered almost the whole frame, over 80%, which aren't very informative.
That makes sense.
But then they added a critical self-verification step.
Self-verification during data creation. How did that work?
Yeah, they used the baseline model itself, Qwen 2.5 VL7B, to check the boxes. For every suggested bounding box and object label, they'd crop that part of the image and ask the model essentially, is this really a object name?
Oh, okay.
They only kept the samples where the verification model said yes with high confidence. So they were pre-filtering the data to make sure the box actually matched the label relevant to the reasoning.
That's clever. It means the data the model eventually learns from is already vetted, internally consistent.
Exactly. And the final stage was just a self-consistency check, making sure the answer, the time, the box, the reasoning trace everything lined up coherently. It's also worth mentioning how they distributed the data. The SFT set for initial training was about half general QA, but the RL set for the refinement stage really dialed up the focus on those fine-grained spatio-temporal samples up to about 30%.
So they eased the model into it.
Yeah, structured the data to gradually increase the difficulty and specificity as training went on.
All right, now for the really tricky part, the training. They started with Qwen 2.5 EL7B. How did they actually teach this model to reliably use this very specific, structured spatio-temporal evidence?
They used a pretty standard but refined 2-stage approach. Stage 1 was what they called cold start initialization, just standard supervised fine-tuning on that STGR COT 30K dataset.
Getting the basics down.
Exactly. Teaching it the basic grounding capability and, crucially, getting it to output things in that very specific structured format we talked about. If the model can't even produce the right format, RL is just going to fail later.
Okay, so stage 1 sets the foundation. Stage 2 is the reinforcement learning, presumably where they push for peak performance. Now, they specifically mentioned using GSPO group sequence policy optimization instead of the more typical GRPO. Why that switch? What's the difference?
Yeah, that's a subtle but really important point for stability, especially with chain of thought reasoning. GRPO, the standard approach, usually works at the token level. It calculates importance ratios and does clipping based on individual tokens. But when you have these long, complex reasoning chains, like linking multiple boxes and timestamps together, token-level stuff can get unstable. If one token early in a long sequence gets a bad reward or gets clipped weirdly, it can throw off the entire reasoning chain downstream. It can lead to what they call catastrophic collapse.
So, like, if the model gets the first 2 steps right but messes up step 3, a token-level approach might destabilize the whole thing.
Precisely. GSPO gets around this by doing its work at the clipping, defining rewards at the sequence level. The whole output, the full reasoning chain, is considered together.
So the reward aligns with the quality of the entire thought process.
Exactly. It gives much more stable training dynamics when you're dealing with these complex composite rewards needed for long reasoning sequences.
Okay, let's dive into the star of the show then, that specialized reward design. You mentioned the thinking reward, CATHOT, combines temporal and spatial parts. And you mentioned this risk of spatial collapse. Can you break that down? What's the challenge there?
Right, the spatial collapse. It's that chicken and egg problem again. To calculate the spatial reward, usually based on intersection over union IOU, comparing predicted versus ground truth boxes, you first need an accurate timestamp prediction. If the model predicts a timestamp that's even a little bit off, especially early in training.
Like a few frames out.
Yeah, exactly. Even just a few frames off the ground truth timestamp. The system might then assume the predicted bounding box at that slightly wrong time is irrelevant, even if it's a decent box. So the spatial reward, $3, just goes to 0 or near 0.
So the model gets no useful feedback on how to improve its spatial production just because its time prediction was slightly wrong. Learning just stalls for the spatial part.
Precisely. It stalls the spatial learning. So they needed a way to give the model helpful, dense feedback on timing first, and then get progressively stricter. And that brings us to their first clever solution: adaptive temporal proximity.
Adaptive temporal proximity. Give me an analogy for that.
Okay, think of it like training wheels for time, but the wheels gradually get smaller and smaller automatically. The temporal precision constraint, they call it sigma, starts out really large, really loose.
So it's generous early on.
Very generous. The model gets a reward signal for timing, even if its prediction is pretty far off the mark. This gives it a stable gradient, something to learn from initially. But then as training progresses, sigma gradually shrinks.
Tightening the screws.
Exactly. It enforces stricter and stricter alignment over time. It guides the predicted timestamps closer and closer to the actual ground truth. This builds that solid temporal foundation you need before you can reliably evaluate the spatial part.
That makes a ton of sense.
Yeah.
Get the timing roughly right first, then zero in. Okay, so what about the second solution? Temporal gating. How does that fit in? It sounds like it connects the timing success to the spatial reward.
Temporal gating is basically the gatekeeper for the spatial reward.
Yeah.
It makes a simple rule. The spatial reward only gets calculated if the temporal prediction is already pretty close to the ground truth time.
How close does it need to be?
They set a threshold, tail, of 3 seconds. So if the predicted time is within 3 seconds of the correct time for that piece of evidence, the gate opens and the spatial reward, the IOU for the box, is calculated. If it's further than 3 seconds away, the gate stays shut and the spatial reward is ignored for that step.
Why do you need that extra gate if adaptive temporal proximity is already guiding the timing?
Good question. It's to prevent rewarding coincidences, essentially. Without the gate, the model might correctly identify, say, a person in the video, but at a completely wrong time point relative to the question being asked. It might find a correct object but link it to the wrong moment.
Finding a relevant-looking box, but at an irrelevant time.
Exactly. The gating stops the model from getting rewarded for finding those irrelevant objects at the wrong times. It forces the model to align both space and time correctly, which is critical for making the evidence trustworthy and boosting that overall interpretability.
Okay, that is some seriously clever reward engineering to solve a really fundamental problem. So the big question, did it work? Did all this effort with the data and the training let Open-o3 video actually outperform the big proprietary models?
Yes, it absolutely did. On that V-star benchmark, which is really designed to test this specific verifiable reasoning, Open-o3 video set a new state-of-the-art. It beat strong, closed-source models, including GPT-4o and Gemini 2 Flash, and those gains were substantial, remember?
Yeah, refresh my memory.
Plus 14.4% in MAM and a huge plus 24.2% in MLGM. And that MLGM metric, the grounded evidence match, is the direct measure of how well it links reasoning to the correct box and timestamp. So those gains really show a massive leap in the ability to provide verifiable evidence.
And presumably this wasn't just a one-trick pony for V-star. Did this grounding ability help on more general video tasks too?
That's the really encouraging part, it seems to generalize. They saw consistent improvements across a range of different benchmarks, like plus 4.1% on long video understanding tasks in video MA, also plus 3.1% on recognition tasks in WorldSense. And even on pure temporal localization, just finding the right time segment, it got a plus 4.5 MIOU boost on TVG Bench. So it seems integrating this explicit, verifiable evidence helps both the high-level reasoning and the low-level perception.
Right. Now, the ablation studies where they turn different pieces off to see what breaks those usually tell the real story. What were the key takeaways there? What really mattered?
Okay, first, the training setup. Combining SFT with RL using GSPO gave the best results. That really confirms that GSPO provides better stability for this kind of complex chain-of-thought reasoning compared to more standard RL approaches.
So the optimization choice mattered.
Definitely. Second, the reward design was crucial. Taking out temporal gating, that gatekeeper we just discussed caused a noticeable drop, 1.4% in MAM, 1.7% in MLGM. That really validates its role in filtering out misleading spatial signals and ensuring the spatial supervision is actually trustworthy.
Makes sense. And what about the data? How much impact did those special 5.9K high-quality samples have?
That was actually the single biggest factor for the grounding performance. Using that high-quality 5.9K annotated data, curated with their careful pipeline, gave a boost of plus 5.4% MAM and a massive plus 10.4% MLGM compared to models trained only on filtered data from other sources.
Wow.
It really hammers home the point. For this kind of evidence-based reasoning, the quality and the structure of your data are absolutely paramount. You can't just throw quantity at it.
Okay, let's touch quickly on how this works in practice. At inference time, the model doesn't just spit out an answer. It gives that whole trace, right?
Sure.
The boxes, the timestamps.
Yeah.
Which sounds like it offers a sort of built-in confidence score.
That's exactly right. They actually use that trace for something called confidence-aware voting at inference. The model generates a few possible responses, each with its spatio-temporal evidence trace. Then it actually crops out those proposed evidence regions from the video and scores how relevant those cropped images are to the reasoning. Then it combines the answers, weighted by these confidence scores. And this method consistently did better than just taking a simple majority vote of the answers like plus 1.0% better on video MMU.
So the grounded evidence itself provides a useful signal for self-verification, even at runtime.
Yes, exactly. It enhances reliability not just during training, but when you actually use the model.
So Open-o3 video seems like a really significant step. It delivers video reasoning that's not just accurate, but also interpretable and verifiable because it forces the model to show its work, link the language to specific boxes and times. That feels crucial for actually trusting these models.
It really is. That verifiability is key. Now, the paper is honest about limitations, of course. It still faces challenges with super long or very complex videos or really small or fast-moving objects, and it doesn't incorporate audio or speech yet. But it definitely provides a strong blueprint for tackling that core difficulty of precise, grounded perception in video.
Okay, so here's a final thought for you, the listener. This framework uses explicit visual evidence, the boxes and times, to generate a kind of internal, measurable self-verification score. We see it in that confidence-aware voting. As these AI models get more powerful, but also maybe more opaque, how could we leverage this idea, this ability for a model to point precisely to why it thinks something? With coordinates. Could we use that signal not just to measure confidence, but to actively detect and maybe even correct hallucinations in real time? If the model's own evidence trace shows low confidence, or maybe the visual evidence clearly contradicts the text conclusion, could that become a mechanism for guaranteed reliability, moving beyond just aiming for accuracy? That leap from just measuring performance to enforcing real-time evidence-based accountability, that seems like a really exciting direction this kind of work opens up.